So आज we will continue from the last topic of haloalkanes and haloarenes. So our today's topic is method of preparation of haloalkanes. Haloalkanes. Okay, methods of preparation. So first we will prepare the haloalkane from alcohols. We will react the alcohols ROH with halogen acid. Halogen acid means HX. Halogen acid, that is HX. HX can be HCl, it can be HBr, can be HI, okay, or HF. These are called halogen acids. So when we react the alcohols with halogen acids, then what will happen? As we know that it will break down in two parts, that H will break in the form of H plus and X in form of X minus, and here we are having alcohol OH. In oxygen we know that there are lone pair electrons, okay. So oxygen will try to donate its lone pair electron to H plus. Alright, so it will form a bond with H plus. So it will become ROH, and positive charge will be developed on oxygen. Alright, and here we are having this X minus. Now this X minus will attack to R, and we will get, and oxygen will try to attract the electron from R, and it will took the electron and remove. So finally we will get the product RX plus H2O. This is how we will get our product. So this is the reaction mechanism. Okay. So in this kind of reaction, there are two types of reaction mechanism we used to follow. First one is SN1 reaction mechanism, and second one is SN2 reaction mechanism. We follow two types of reaction mechanism. First one is SN1 reaction mechanism. The full form of SN1 is substitution nucleophilic unimolecular reaction mechanism. See, this is your nucleophile. Okay. And this OH minus is also nucleophile. And second one is SN2, that is substitution nucleophilic bimolecular reaction. Okay, so two types of reaction mechanism we used to follow in this type of reaction. Alright, see here, if we follow this SN1 reaction mechanism, so in this type of reaction, intermediate carbocation is formed. First of all, just look at this mechanism. After that, I will discuss both of reaction mechanism. So basically what happens here, whenever we react this alcohol with HH, that is halogen acid, the H plus oxygen donates this electron and form a bond with H plus, and this X minus that is nucleophile, it will attack to the R and it will get attached with R, and this water will be get separated, and this is how we will get the RX, that is haloalkane. Now we will discuss this both type of reaction mechanism. All right, see here. First one is SN1, that is substitution nucleophilic unimolecule. In SN1 type reaction, we used to take 3-degree or 2-degree carbon compound. Like if we are having a 3-degree, like carbon, 3-degree carbon, that is CH3, CH3, and CH3. So here we are having a 3-degree carbon compound, and now we are reacting this 3-degree carbon compound with halogen acid, that is HX. Okay. Now what will happen? The reaction will process in 2 steps. In first step, step number 1, what will happen? This will break down in the form of H plus and X minus. Okay. Again, the oxygen will donate its electron to the H plus and it will form a bond with H plus. Okay. So what will happen here? So in step 1, what happens? Carbocation forms. So you can say in step 1, formation of carbocation, formation of carbocation. Carbocation is formed out this carbon, this 3-degree carbon, oxygen and hydrogen will get attracted and this O plus will be formed. So oxygen will donate its electron to H plus and develop a positive charge. Okay, this is how. Now the oxygen will take the electron from the carbon. Oxygen will take the electron from the carbon and get separated from the compound. So finally we will get a carbocation, that is C plus, C plus, CH3, 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 C plus, and H2O will be separated. So this is the our carbocation. This is our carbocation. So in the first step, what happens? The carbocation is formed. This carbocation is stable carbocation because it is a 3-degree carbocation. It can take the electron from any of the carbon. So that is why we prefer 3-degree or 2-degree compounds, because during the formation of carbocation, that carbocation should be stable. Okay. So more degree carbocation, it will more stable. Alright. So this is our first step. In the next step, what happens in step number 2? Step 2. Attack of nucleophile. Attack of nucleophile. Attack of nucleophile. So here, as you can see, X minus is left. That X minus will now attack on the carbonation. Okay, this X minus is your nucleophile, so it will attack to the carbon. So now X minus will attack to the this carbonation. CH3, CH3, CH3. Now X minus will attack, so it will form a RX. So finally we will get the product RX. Okay. So this reactions processed in two steps. In first step it forms a carbocation. In second step the nucleophile attack to the compound and it will form finally product, that is RX. Okay. Two, three more things we can discuss here. In SN1 reaction, the rate of reaction is directly proportional to the Rx, that is the concentration of the reactant. Okay, so it only depends on the concentration of the reactant, that is one molecule, that is why it is called unimolecular. Okay, and in this reaction carbocation is also formed. Carbocation is formed, and the reactivity for SN1 reaction follows 3 degree, then 2 degree, then 1 degree. And for SN1 reaction we normally use polar protic nucleophile weak acid, weak base nucleophile. Okay. And in SN1 reaction rearrangement is possible. Rearrangement is possible. I will explain you how. And SN1 reaction also there is a racemization or racemic product we can get. Racemization product. Okay. See, polar protic means the nucleophile which is having H plus, means in polar protic nucleophile you can take CH3OH, okay, or H2O or CH3CH2OH. These are called polar protic. Okay, polar protic nucleophiles. In SN1 rearrangement is possible. How rearrangement is possible? See here, right? If we are having a compound like this, that is C 3 degree carbon, CH3, 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 and further we are having a 1 degree carbon, CH2, and X. Now, and OH. Now, if we react this kind of reactant with HX. Okay, this kind of reaction. As we know that when the OH will get separated from this carbon, X will now attack to this carbon, but this carbon is a 1 degree carbon, and we know that the reaction only carbocation is only stable at the 3 degree. What will happen? The OH will donate its electron to this oxygen and it will get separated from here. Positive charge will develop here. So carbocation forms in 1 degree carbon. So that 1 degree carbocation is unstable. Okay. So what will happen here? In this kind of reaction, because reaction only prefers the 3 degree carbon, this CH3 will remove from here 3 degree carbon and it will form a positive charge here, and this CH3 will get attached to this carbon. Okay, this CH3 will get attached to this carbon. So finally, after the rearrangement, you will get the product like CH3, CH3, positive charge, CH2, and this CH3 will get attached here, CH3, okay, plus HX. This is how it will get rearranged. This OH minus and H plus will get separated from here. Okay. Now this nucleophile X minus will attack directly to the 3 degree carbon, not to this. So now X minus will directly attack to the 3 degree carbon. So now this carbocation is a 3 degree carbon which is a stable carbon. So this kind of rearrangement is possible in SN1 mechanism. See what happens here. We are having a 3 degree carbon and 3 adjacent carbon of 3 degree carbon is a 1 degree carbon. Okay, and we are reacting this reactant with the halogen acid. So what will happen, because this is a 1 degree carbon, this is an unstable carbon. So what will happen, one CH3 will remove from here and get attached to the this carbon. This is also called hyperconjugation. Okay, the rearrangement will take place, and now the 3 degree carbon will generate a positive charge. Okay, and now X minus can attack to the 3 degree carbon. Okay. So this is how rearrangement is possible in a 3 degree in SN1 mechanism. Alright. Next one is racemization. What is racemization? See, optically active product, optically active organic compound are able to rotate the PPL light from left or right direction. Okay. In racemic product, the optically active compound can rotate the PPL light 50% left side, that is called levorotatory, and 50% of organic compound can rotate the PPL light from the right side, that is dextrorotatory. And so overall the organic compound, the rotate the PPL light 0 degree. So that is why the both levo and dextrorotatory organic compounds are formed. That is why both product in a combined form we called the racemic mixture, and this process is called racemization. I will explain you in the next part. After explaining you the optical isomerism. See how the racemic product is formed. Wait a minute. Before that racemic mixture, let's understand the SN2. In SN2 mechanism, we follow this 1 degree, then 2 degree, then 3 degree product carbon. Why 1 degree? When we take a 1 degree carbon compound like CH3OH, okay, and react this 1 degree carbon compound with HX, H plus, X minus. Now again what will happen? This oxygen will donate its electron to H plus. So in first step, step number 1, what will happen? This CH3 and this oxygen will donate its electron to H plus. Now at the same time, this X minus will attack from the rear side of the compound. This is called intermediate product. So this reaction will placed on a one step. Will happen in only one step. Okay. At the same time, the oxygen will get attached with the H plus and the nucleophile will attack from the rear side and it will form a intermediate product. This is called the intermediate product. Intermediate product. Why it happens so? Because we take always in SN2 type mechanism we use a strong nucleophile like polar aprotic nucleophile like CH3O minus, Cn minus, C2H5O minus, OH minus. These are the strong nucleophiles, so they don't wait for the formation of carbocations. They attack immediately with the reactant. Because they attack immediately with the reactant, that is why they form an intermediate product. And after the separation of oxygen, finally we can get the haloalkane product, that is CH3X plus H2O will get separated. So because this reaction takes place in only one step, and these nucleophiles are called polar aprotic. Polar aprotic. Polar. That is why the rate for the SN2 type reaction is directly proportional to the reactant, that is Rx, and nucleophile, because nucleophile is also taking place at the same time. So because the rate depends on the two molecules, that is why it is called bimolecular. Bimolecular. In this type of reaction, rearrangement is not possible. And it forms a inversion product. Because here the nucleophile attacks from the rear side. That is why it is called the inversion product. It forms a inversion. Always it forms a inversion product. Yeah. In this kind of reaction, carbocation does not form. No carbocation form. No carb. Okay. So this is the reaction, and for SN2 type reaction we use strong nucleophile, strong base, polar aprotic nucleophile, polar aprotic nucleophile. So this is all about the SN2 type of reaction. So one thing always you have to remember, in SN1 type of reaction the carbocation is formed. So we prefer the 3-degree carbon then 2-degree carbon, and in SN2 type of reaction we usually prefer the 1-degree carbon and strong nucleophile. Okay, so our next topic is optical isomerism. Optical isomerism. Isomerism. What is optical isomerism? Okay, see, first of all, you have to understand the plane polarized light. What is plane polarized light? Plane polarized light. In short, we also call it PPL. PPL light. Okay, what happens when the normal light propagates? See, like you are having a source of light, that is bulb. Okay, so when we light the source of light, the light will propagate in all the directions. The light will propagate in all the directions. Okay, but when you placed a Nicol prism or polarizer in the path of light, when you place a polarizer or Nicol prism in the path of light, so it will block the light of the all the directions and only passes the light. See here, this is a polarizer. It will allows only the vertical side of light. Okay, it will only pass the vertical side of light. This is how, actually this is mechanism. This is your polarizer. Now you see there is a gap between the parallel lines, perpendicular lines, and these lines will only allow to pass the light which is perpendicular to the propagation. Okay, so we will get the light, only that light which will pass through that polarizer, and it will block all the directions of light, like this direction, this direction, this direction, this direction. Light are here, light are propagating of all side, here, this direction, this direction, this direction, and this is your perpendicular line. So it will only allows this direction light, that is a perpendicular light, this perpendicular light, which is the perpendicular to the direction of propagation. So here only we will get a light which will propagate only one direction, that is perpendicular to the perpendicular to the direction of propagation. So whenever we put a polarizer or nickel prism in the path of light, so that polarizer will block the all directions lights and allows only one direction light to pass through it, and that one direction light is called plane polarized light. That plane polarized light is perpendicular to the direction of propagation, that is the or perpendicular to the propagation you can say perpendicular to the plane of the propagation. See, light is propagating which side? This side. Light is propagating this side. The light is going through like that here, but the polarizer is blocking the light from this side. These lights are blocked. These lights are blocked. So only the light which is perpendicular to the plane, that is perpendicular to the plane, is able to pass through it. Okay, that is called PPL light. All right. Now if we put an organic compound in the path of that PPL light, so organic compounds few organic compounds are able to rotate that PPL light. When these PPL lights are passed through this this is organic compound. Only few organic compounds are able to rotate that PPL light to the left direction or the right direction. If they rotate the PPL light to the clockwise direction, they can rotate the PPL light from the clockwise direction or anti-clockwise direction. Okay. So based on their rotation of the PPL light, if the organic compounds rotate the PPL light in clockwise direction, so they are called dextrorotatory. They are called dextrorotatory. If they are rotate the plane polarized light in clockwise, so they are called dextrorotatory. Or denoted by plus sign, or if they rotate the light in anti-clockwise, they are called levo-rotatory, or denoted by minus sign. So based on their rotation of PPL light in right clockwise direction or anti-clockwise direction, they are called optically active organic compounds. The organic compounds, when they are put in the path of PPL light, if they are able to rotate the PPL light in clockwise or anti-clockwise direction, then they are called optically active organic compounds, and that property of that compounds are called optically activity, and they are called optical isomers. Okay, so how you will define the optical isomerism? See, those compounds having the same formula and even the same property also. Those organic compounds, those organic compounds which are having the same formula, same structure, same structure, and approximately same property, but they differ differ only differ only in rotating the PPL light in opposite direction, in opposite direction. Then they are called optical isomer. Then they are called optical isomer isomers. Okay. So organic compounds which are having the same formula, same properties, same structures, but they differ only in the rotation of PPL light in opposite direction. But if they are rotating the PPL light in opposite directions, then they will consider as a optical isomers. All right. See, if the optical isomers and its mirror image, let us consider you are having a optically active organic compound like this CH3OH ClBr. Okay, and this is your optically active organic compound, and the mirror image of this compound is CH3OH Br, right, forming BrOH and Cl. This is its mirror image. Now, if the optically active compound and its mirror image are forming, are rotating the light, PPL light, in clockwise and anti-clockwise direction, then both the compounds are called the enantiomers. Okay, so you can write if the organic compound, organic compound and its mirror image rotate the PPL light, PPL light in clockwise and anti-clockwise direction, then they are called optical, they are optical isomer They are optical isomers and are called enantiomers. Okay. So if the organic compound and its mirror image are rotating the PPL light in clockwise and anti-clockwise direction, then both are called the enantiomers. Okay. So one more thing you have to understand, that the mirror image of the optical compound should be non-superimposable. That is, the carbon compound should be in asymmetric structure. The carbon should be asymmetric. That is asymmetry. Okay. Means the carbon should be attached with the four different kind of elements. When the carbon is attached with four different compounds, then that carbon is called the chiral carbon. Chiral carbon. So the mirror image is only possible for asymmetric carbon, that is chiral carbon, and the mirror image of that chiral carbon is non-superimposable. So the image should be non-superimposable. What is non-superimposable? Like non-superimposable. Like if I put my palm in front of mirror, it will show the mirror image of like this, and they both are non-superimposable. If I put both the image on one another, they are not able to cover. Okay, that is called non-superimposable. So this is possible only in asymmetric compound. So for that we use a chiral carbon. Chiral carbon, in chiral carbon four different compounds are attached, and it will form a non-superimposable mirror image. So this kind of organic compounds which are showing the optical isomerism, they are called the enantiomers. Or organic compound which forms a non-superimposable image, they are called enantiomers. Enantiomers. Okay. Now let's talk about the racemization or racemic mixture, what we have left in the previous part. Okay, see. Racemization. If we are having a chiral carbon, now we are having a, let us consider we are having a chiral carbon, Cl, C2. Now if this chiral carbon is attacked by halogen halide, halogen acid, now what will happen? This H plus X minus. Okay. Now this oxygen will donate its lone pair electron to this hydrogen, and this nucleophile will attack to the carbon. Now that nucleophile can attack from the both sides. This is your 2-degree carbon. So SN1 mechanism will follows. So in SN1 mechanism, the nucleophile can attack from the both sides, from the front side or from the rear side. So if it attack from the front side, so the product will be formed like this: CH3, C2H5 and H and this X. Okay. Now this C2H5 is behind the carbon. Okay. This is not on the left side. This is the inside of the carbon or behind the carbon. Now if the X is attacked from the rear side, that is it can also attack from the rear side. So the product will form CH3 X H C2H. So here two kind of product we can form from the when the X is attached from the front side. This is called the retention product. This is called the retention product, where the X is retaining the position of OH, and when the X is attached from the rear side, this is called the inversion product, where is X is attached from the reverse side, that is called inversion product. So if this retention product is rotating the PPL light to the clockwise, so 50% product is retention product we can form and 50% inversion product we can form. Okay, so if the 50% product is rotating the light to the clockwise and 50% inversion product rotating to the light in anti-clockwise, so the overall product will cancel the rotation. So finally there will be no rotation in PPL light. So this type of mixture of product is called racemic mixture. This is called the racemic mixture. Racemic mixture. So here what happens? In SN1 mechanism, both kind of product we can form, the inversion product and retention product, and both can rotate the light in clockwise and anti-clockwise direction. So the overall rotation will be zero or no rotation will take place. So in that condition, we said this is the mixture of racemization. This process is called racemization, and the mixture of these products are called racemic mixtures. Alright, so this is possible only in SN1 type of reaction. Let's talk about the SN2 type of reaction. So here the compound is optically active, then also there is no rotation is taking place because of racemization. When the no rotation is take place, then at that condition we called it a meso product. Meso product. If the organic compound rotates the PPL light in clockwise direction, then it is called the dextrorotatory. If the organic compound rotates the PPL light in left anti-clockwise, then it is called the levorotatory. And if the organic compound does not rotate the light, at that condition we called it a meso product or meso compound. Okay. Next is Walder inversion. Next topic is what it is saying. Walden inversion. Walden What is Walden inversion? Walden inversion states that in a SN2 mechanism where halogen is attached to one degree carbon. Okay. In SN2 mechanism, when it is reacted with halogen acid H plus X minus. Here what happens? X will attack to the carbon, or X can able to attack to the carbon only from the rear side. This CH3 is the back side of this carbon. Okay? So it can only attack the carbon from the rear side. So the product formed, only inversion product we can form here. CH3, and here X will be there. OH and H2O will be removed. So this is the inversion product. So this is called Walden inversion, because in SN2 type of mechanism, the nucleophile can able to attack the carbon compound only from the rear side, and that is why it is able to form a inversion product. That is why it is called a Walden inversion. Okay, so only in SN1 mechanism retention and inversion products are possible, but in SN2 mechanism only inversion products are possible. Why is it so? As you know that in SN2 mechanism we use the strong nucleophiles, so it will attack immediately. Okay, it does not wait for the formation of carbocation. Okay, so it will immediately attack to the carbon from the rear side. All right.